So in our last lecture, we made a change to Maxwell's equations, and we incorporated in Maxwell's equations the effect of a time-varying magnetic field in the following way. Okay, so here is our new Maxwell equation in differential form. It includes the special case where dB dt is 0 and therefore the curl of E is 0. That's our electrostatics problem. In integral form, it looks as follows, and this law says the following. If I have a loop in space, it might have a wire going around it, it might not. So there we go, there's some path in space. So let's say this has some magnetic field going through it in the following form. Alright, so it's cutting through that area. If I calculate the integral of E dot dl around the loop, so I'm going to calculate the integral of E dot dl around this loop, that must equal minus d dt of the integral of B dot dA going through the loop. So here is our B field going through the loop. Alright, now, importantly, let's say B dot dA is non-zero, but it's constant in time, then the integral of E dot dl will be 0. Okay. If, however, we have a magnetic field which is going through this loop and its derivative, and it has a non-zero time derivative, in other words, this quantity on the right-hand side is non-zero. So the magnetic field is changing, the flux of the magnetic field through the loop is changing, then the integral of E dot dl will be non-zero. And if this were a wire, let's say this were a wire that could carry a current, if the integral of E dot dl is non-zero, a current will flow in this wire. So a changing flux of field through the loop defined by the wire would drive a current in the wire, and that current would be proportional to E dot dl and inversely proportional to the resistance of the wire loop. All right, this is the meaning of this of these equations here. Okay, so we're going to solve a problem. I think this is a Griffiths problem. It's problem 7.17, I believe, in Griffiths. And it's quite a nice illustration, even though it's somewhat artificial. It's quite a nice illustration of how we might use these equations. So the problem is defined by the following picture. Okay, so what we have here is a long solenoid where the length of the solenoid is large compared to its radius. We're going to come back and discuss that in some detail later. And this is carrying current I, and this produces, the long solenoid, you would have studied this in first year, produces a magnetic field inside the solenoid. I'm going to call this the Z direction, Z hat direction. Inside the solenoid, this would produce a magnetic field of the following form. Okay, so the magnetic field inside the solenoid is proportional to the current, and it's proportional to the number of turns per unit length. And if you look at the units for this has the right units. Mu naught times current divided by a length. Outside, the magnetic field for a long solenoid is 0. Now this wire goes around the solenoid. It's not in electrical contact with the solenoid. It has a resistance R here. If I were to take the integral of E dot dl around this path here, then it would equal minus d dt of the integral of B dot dA. We know that from the previous equation. Alright, so loop 1, by loop 1 here, I mean this loop here. This is loop 1. Well, B is given by the magnetic field in the solenoid, and if I were a function of time, B will be a function of time. This derivative will be non-zero. The integral of E dot dl will be non-zero, and will drive a current through this wire here. This is effectively a transformer. That's what this is, and we'll have a look at that in more detail in a bit as well. So in the particular case where the current flowing in the solenoid, for example, was equal to some constant times time, let's calculate the current flowing in our loop 1. Let's do that. Okay, so in this case, our magnetic field B has the following form. All right, and so the integral of B dot dA, remember dA here for this loop is in, for loop 1, dA is in the z hat direction, so this is or we can make it in the z hat direction, we can certainly do that. This is a loop that all lies in the same plane. We could make it circular, although that's not critical. The integral of B dot dA then becomes the following. Okay, so you might say, why is it pi a squared, where a is the radius of the solenoid? Well, the reason for that is that the magnetic field is zero outside the solenoid. It's only non-zero inside the solenoid. So from this result, we can now calculate the negative time derivative, and we can calculate the integral of E dot dl. So let's do that. Okay, so now the current that flows in loop 1, I'm going to call that I1, would be the integral of E dot dl divided by the resistance. All right, so this is our result then for the current flowing in loop 1. You'll notice that if K is positive, that is the magnetic field in the solenoid is increasing with time, I1 is in the opposite direction to the current in the solenoid, and if K is negative, that is the magnetic field is decreasing with time, I1 is in the same direction as the solenoid. And you can have a think about that in terms of Lenz's law that you will have come across in your first year lectures. Okay, so we're going to leave this problem here, and we're going to, in the next segment, delve a little bit into the infinite solenoid and have a little bit of a look at some of the subtleties behind these arguments that the magnetic field is constant inside the solenoid and zero outside the solenoid. And then after that, we're going to return to the kind of problem we've just studied here and have a look at transformers.